In this video, we're going to compute the moment of inertia of a solid sphere about its diameter by using our previous result for the moment of inertia of a thin cylindrical shell. And as we can see, that previous result for a thin cylindrical shell of mass little m and radius little r is that the moment of inertia turned out to be mr squared. And I'll post a link to the video where that formula was first derived. Now, just a quick warning before we begin. This is not the easiest way to derive the moment of inertia of a solid sphere, because the resulting integral requires a trigonometric substitution. However, this example provides a great review of physical integration and trig subintegrals in particular, and I think it's just more fun to do it this way. So here's the idea for how we're going to break this sphere into infinitesimal moment of inertia contributions. We're going to nest cylindrical shells to build up the entire sphere. So if we use an x for the radius of this particular shell, I want to make it clear just how the nesting occurs. When x is close to 0, that means our shells are very tall and skinny, and they have a height very close to the diameter of the sphere. Then when x is close to r, the shells are really short and really wide, with a diameter that's close to the diameter of the sphere. So as x goes from 0 to r, we can build up this entire sphere, and those are actually going to be our limits of integration on this thing. X will go from 0 to r. So we want to get the dimensions of our arbitrary shell labeled here, and we've already decided to use x for the radius. This means we're going to use a dx for the thickness of the shell. That's a small increment in x, giving us the infinitesimal thickness of the shell wall. Next, we want to express the height of the shell in terms of x, and we start by realizing that the distance from the center to the point at which the shell touches the outer surface, that's still big R, the radius of the sphere. And this allows us to find half the height of the shell using the Pythagorean theorem. So that turns out to be the square root of r squared minus x squared, because if I square that thing and add it to x squared, I'm going to get r squared and satisfy the Pythagorean theorem. Now, ultimately what we want to do is find the mass of this shell in terms of x, and that will allow us to find the moment of inertia contribution of the shell. The mass is a differential quantity, so we'll call that dm. And dm is given by the density multiplied by the volume of this cylindrical shell, and we call that dv because it's an infinitesimal volume. So to find dv, we're going to cut the shell vertically and unroll it into a rectangular slab. The thickness of this slab is dx. The height of the slab is twice the square root of r squared minus x squared. And the length of the slab, that corresponds to the circumference of the original shell when it was rolled up. So that's 2 pi x. So to find the volume of the shell, we just multiply all three of these dimensions, and we get a differential volume of 4 pi x times the square root of r squared minus x squared dx. Now that we have that dv figured out, we can get dm by just multiplying it by rho. And this means we're ready to write down the moment of inertia contribution of this shell. So that contribution we'll call di. It's an infinitesimal contribution to the total moment of inertia. And it's given by the mass of the shell, which is dm, times the radius of it squared. So there I'm simply plugging back into this formula for the moment of inertia of a thin cylindrical shell. So we're just going to replace dm with the density rho multiplied by this expression for dv. And when we do that, notice that we end up with an x cubed in this expression. We had an x squared coming from our moment of inertia formula and another x that came from the expression for dv. So I end up with 4 pi rho x cubed square root of r squared minus x squared dx. And now that the moment of inertia contribution of a single shell is expressed entirely in terms of one variable, x, this means we're ready to use a physical integral to add up all of these contributions. So we start by saying that the total moment of inertia is the sum of all the moment of inertia contributions. That's what an integral does. It's a summation device for adding up a bunch of continuously changing infinitesimal quantities. And all we have to do is plug in the formula for di that we figured out, and we end up with an integral that's starting to look pretty intimidating. So notice the interior of this thing, that's just my expression for di, and then my limits of integration, because x is the integration variable. My limits of integration go from 0 to r. The lower bound there representing those tall, skinny cylindrical shells that I get when x is very small, and the upper bound representing those short and wide cylindrical shells I get when x is getting close to r. So that's it on the setup, and now it's time to put our calculus hats on and grind through this integral. So I notice in this integral that this square root is a major complication, and there's a common trick for simplifying the square root part. I'm going to make a trigonometric substitution here. I'm going to say let x equal r sine theta, where we're just introducing a new variable theta that will become our integration variable. And the point of this is that x squared is then r squared sine squared theta. That allows us to find a 1 minus sine squared theta inside the square root, but that's cosine squared theta, and the square root of that is just cosine theta. So there's our basic plan. There will be some complications as a result of making this substitution, but this is our basic plan. Now remember, when we make a trig substitution like this and start to transform our integral to theta space, we also have to transform the differential itself, dx. So dx here is going to be the theta derivative of this, that's r cosine theta, multiplied by d theta. I'm also going to transform the limits of integration. This is the lower bound on x and the upper bound on x, 0 to r. I want to transform those to theta limits so that we can just forget about x completely after we make this substitution. So when x is equal to 0, I can see in my definition for my substitution here, when x is equal to 0, it means that sine theta is equal to 0, and that happens when theta is equal to 0. When x is equal to r, that means r is equal to r sine theta. If I divide both sides by r there, I find that sine theta is equal to 1, and this happens when theta is equal to pi over 2. So let's make all these substitutions in our integral and just move to theta space from here on out. My integral is now going to go from 0 to pi over 2. Those are limits of integration on theta. I have a 4 pi rho in this integral. And then there's an x cubed, which is then r cubed sine cubed theta. And then we have this square root of r squared minus x squared. So r squared minus r squared sine squared theta. And then dx itself has to be transformed, and that was r cosine theta d theta. So the next thing I'm going to do is factor out an r squared from inside of this square root. That gives me a factor of r outside of the square root. And then that 1 minus sine squared theta can be replaced with a cosine squared theta, but the square root of that is just the cosine of theta. So we're going to handle all these things in the next step. At the same time, I'm dealing with all the constants. So I'm going to move a 4 pi rho r cubed out in front. We get another r out of the square root, and we get another r from the r cosine theta d theta at the end. That's a total of 5 factors of r. So we're going to start by writing 4 pi rho r to the 5th, and then we have the integral as theta goes from 0 to pi over 2. And I had a sine cubed, and then out of the square root, I'm obtaining a cosine, and then we have another cosine at the end. In other words, this becomes the integral of sine cubed theta cosine squared theta d theta. And this is a pretty standard trigonometric integral. What I notice is with this odd power of sine, I could split off a factor of sine squared out of that and end up with just a lonely sine of theta. And then what our plan is that we're going to use a trig identity to transform sine squared theta in terms of a cosine squared theta. And then this lonely leftover factor of sine theta, well, that's the derivative of the cosine function, and it allows us to use the chain rule backwards. Another way to say that is it gives you the right differential to do a u substitution. Okay, so as I wrote down that step, I moved our lonely sine function toward the end of the integral, and everything else in front of that is these powers of cosine. So when I distribute the cosine over my parentheses, I end up with a cosine squared minus cosine to the 4th. And I'm going to put in one more tiny step just to highlight how the chain rule is working backwards here. So what I'm going to do is distribute the sine function into these parentheses. And what I'm trying to point out here is that we have a power of the cosine function. We have cosine squared, and then we have the derivative of the cosine function, which is almost sine theta, but we missed by a minus sign. A similar thing is happening in the second term. We have cosine to the 4th multiplied by the derivative of the cosine function. Almost, we're just missing by a minus sign. So you can do an explicit u substitution if you like, but the chain rule backwards is really guessable here. And I'm just going to guess our antiderivatives. And in my first term, I end up with a 1/3 cosine cubed theta. But that doesn't quite do it because we still missed by that minus sign. That term's actually going to be negative. And I encourage you to just at least check this answer in your head by differentiating it. If you differentiate cosine cubed, you get 3 cosine squared multiplied by the negative of the sine function, and you end up with the original term that was in our integrand. A similar thing is going to happen in the second piece, except in this one, we already have the minus sign we need in the integrand. I end up with a positive term here of 1/5 cosine to the 5th theta. And we're evaluating all this as theta goes from 0 to pi over 2. Now the cosine of pi over 2 is 0, so both of these terms vanish in the upper limit. The cosine of 0 is 1. When we subtract that lower limit, we end up with a positive 1/3 minus 1/5. Well, 1/3 is 5/15 and 1/5 is 3/15, so I get 2/15 in those parentheses. And I'll combine that with the 4 out here while we're going. I end up with 8/15 pi rho r to the 5th. Well, that doesn't look familiar yet for a formula for the moment of inertia of a sphere. And the reason why is that we still need to express this density in terms of the geometry of the sphere. So density is mass per unit volume. And we were told the mass of our sphere was m. We used a capital M for that. And the volume of a sphere is 4/3 pi r cubed. And then just to write this as a single fraction, I could say 3m over 4 pi r cubed. So we're going to take this expression for our moment of inertia and replace the density with 3m over 4 pi r cubed. And then we start to clean things up. I can cancel a factor of 4, leaving me with a 2 in the numerator, cancel a factor of 3, leaving me with a 5 in the denominator. So all these numbers turn out to be 2/5, and we're starting to recognize something familiar here. Our factors of pi cancel. I end up with an m in my final answer, and then 3 factors of r cancel, leaving me with an r squared. So there's our usual formula for the moment of inertia of a solid sphere rotating about one of its diameters. You can definitely say we did that the hard way, but it's an instructive process to have to deal with a trig subintegral occasionally. One last comment on this is that you should make sure a formula for the moment of inertia always has units of kilogram meters squared. And I have this factor of m here giving me my kilograms, and 2 factors of r giving me my meters squared, so the units are good. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Slab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.